Okay, thanks for the introduction. So I'm going to present you the result on our analysis on the security of the schemes that we saw. So this is a joint work with Jean-Charles Faugère. Actually, Jean-Charles did most of the work, but he was not able to be here today. And just quickly, so I used to be at Sorbonne University, but now I'm starting a new project. So it's a startup which is called CryptoNext Security, and we are interested in the design, analysis, and implementation of post-quantum schemes. And in fact, we start to integrate this software into the blockchain. But before doing that, I was mainly involved in trying to attack a scheme. So now I switched to a little bit the design, because attacking a mathematical primitive is not a good way to do a business. And so that's why we got very excited and very interested when we were aware and we were contacted by Eli to analyze the security of this Stark-friendly primitive with respect to algebraic attacks. So it's kind of at the intersection of several topics which was very interesting for us: post-quantum crypto, blockchain, and algebraic attacks. So in this talk, I will start to explain you a bit what is the general methodology that we follow to analyze the scheme. And after, I will present you our results on the ciphers that I propose. And another point, which is not always so nice when you do an attack, is that usually you deliver bad news and people hate you. So today it's okay. So I have not too many bad news, but kind of good news, because we know how to estimate the parameters. We have new techniques to estimate the parameters with Gromner basis techniques. And so, as you saw here, at the end, so all the ciphers that has been described so far, so express quite naturally as a set of algebraic equations. So the task is to understand what is the hardness of solving this equation with Gromner basis techniques. And the first important point to understand is that computing a Gromner basis, in fact, at the end, is not your goal. What you want is to find the solution. So you want to compute the variety which is associated to the system. And so Gromner basis is a way to get this object. And in practice, it's called the zero-dim solving. When you have a finite number of solutions, we are doing this in two steps, two separate steps. First, you compute a Gromner basis with respect to a total degree. And after, you do a change of ordering on this Gromner basis. So you get a lexicographical Gromner basis, which will have this shape. And so from here, you can see that you have a univariate equation in one variable. So you can find the projection on the solution on these variables, and you iterate this process to recover the whole variety. So technically, this means that, in fact, Gromner basis depends on the ordering that you consider on the monomials. And in function of the ordering, you have different property. So computing a Lex Gromner basis allows you to compute the variety. And computing total degree ordering is an easy order, free-handly, computationally order to do in practice. So that's why we always do these two steps. And in fact, in most computer algebra systems, you don't see these two steps. And don't understanding these points, you can maybe miss some points. So from a computational point of view, the cost of these two steps are given here. So the first step is exponential in some degree, so which is called Dmax. So it's maximum degree reached during the computation. And the second step, to get the variety from the total degree Grobner basis, is a polynomial in the number of solutions. Still in practice, and in particular in the case here, this d can be exponential in the parameters. So here are the methodologies that we have, and what we did is to focus on trying to bound this d, the number of roots, because once you have this number of roots d, then you have the cost of the second step, and you have also an upper bound on dmax. And so more or less, if you have a good modeling, so these steps should not be more costly than the previous step. Okay, that's the philosophy. And so in general, when you deal with a block cipher, in fact, it's very difficult to perform experiments because, let's say, for AES, you have dozens of variables, and you don't know how to do small experiments. So you have no idea what is going on for small values, and you have no ideas on how to predict the behavior for a large value, which means predicting this number of solutions. And so here, we have been able to give new bounds on the complexity, and also to provide reasonable experiments to back up this result. So we investigated this list of ciphers, which has been described before. And the method is as follows. So we first have a reference Sage code. So we did an implementation in computer algebra system, so which is Maple and Magma, because on it you have efficient Grobner basis computation. And we have also a dedicated C software. And so we implement some of the algorithms, some of the techniques that we discover in C. And so the method is as follows. So the goal is to estimate the degree, the number of solution of the system, so the maximum degree of the univariate polynomial in the Lex Grobner basis. And we have two separate cases. So for when you have, with respect to the ciphers that we consider, the first one is when you have only one element as an input, and sometimes we have more than one element. So you proceed with more than one element. So this is the M that I mentioned. So for M equal 2, we can assume that you can do the linear algebra in quadratic time. So the goal was to predict the number of solutions in function of the parameters and try to fix the bounds. And for this, we use the shape of the system and some well-known theoretical bound called multi-homogeneous Bezier bound on the number of solutions once we have the good modeling. And so, in fact, we have some proof for the bound and some experiments backing up this. And another thing which was interesting is that when, in some special case, we were able to do the linear change of variables in a linear time. So it means that the complexity is just linear and not quadratic in the number of solutions. And this is completely new. Mm-hmm. So this is a summary of the results that we got for the scheme. And so the first generation is Jarvis. So we put the number of fronts which was recommended by the authors. And this is the new bounds that we obtain with all these tools. So Jarvis, we saw it's the first generation. After we have a new generation, so a rescue So I think paper was never public, but still we investigate that. And so we saw progress in the design, and in particular, the number of rounds increased. And so, in fact, all this work was done in parallel. So we have teams working on their own analysis of the block cipher, and also us trying to understand. And you can see here, for example, that for rescue, we are still, so we are approaching the bound recommended, but we are not able to break the scheme. So let me mention that also in parallel of what we did, Dimitri and Martin Schobnegger also did an algebraic cryptanalysis of Jarvis. So what they obtain is that the number of rounds should be bigger than 19. And so for us, we have a different bound because there is two reasons. Because we can do the change of ordering in linear time, and we have a better bound on the number of solutions. But one part is common, is that the first step was a good modeling, which was also in this paper. And we have the same bound for MIMC. And so when we have rescue here, so for vision, when we implemented this attack, we realized that there is something strange. So when we compute the Gromner basis with respect to a Lex ordering, we have this shape. So this is not the shape that we expect for a zero-dimensional system. And this means that, well, there is something strange here. There is many parasite solutions, so, but we have been able to tweak the modeling to remove this parasite solution and get new bounds on the number of solutions that you have here. So, and for vision, so the number of, so the size of the input, it has more than 2 elements. And so here, one open question is to understand whether we can do the linear change of ordering in linear time. Okay, that's good, because after it's my conclusion, so we have been able to push the practical experiments with our implementation. So to verify that it matches with the bounds that we have in theory, so we can be quite confident on the bound. So as a conclusion, I would like to thank StarkWare Industries for sponsoring this work. And I think more importantly, to bring this to the community and to put this public and say, okay, try to analyze, and we will see if we can deploy this at large scale. So I think this is a very good way to design a cryptographic primitive. And so we have a bunch of new results. So we have kind of the same type of result on StarkCAD and Poseidon. So we have bounds which also take into account the fact that you have full rounds and partial rounds. So there is still ongoing work, so it's very new. And as we discuss about deploying this and trying to find the optimal parameters, my recommendation is to assume that the linear change of ordering can be done in linear time to be on the safe side. Questions? So the question, if I can comment about other types of attack. So the reply is not too much. So we kind of really focus on algebraic attack. So the point is that for this cipher seems to be the most dangerous attack, but we did not compare to other attacks. But at least when we have been able to break the scheme, so it's broken. And for the other one, sometimes we are close to the bound which was proposed, and sometimes was a bit more still improvement. But another thing that I want to say is that here it's a very powerful attack with respect to the different attacks that I consider it for block cipher, because we are only considering one cipher, one ciphertext and one message, and we try to recover the key or to find the pre-image. So just one pair and try to recover. That's a very strong assumption on the attack.
We have to take the rest of the questions offline. Okay, so thank you, Ludovic.